Hi all, and welcome to week 2 of Honors Math Theory. Hopefully you've updated your planner or whatever organizer you're using from the weekly calendar, which will be extremely helpful. As a reminder, you have until the end of the week to complete all of these assignments and check things as needed in the back of your textbook/reader binder. If you have questions, put them in the homework nomination form if it's just on some of these. You can also grab an appointment slot and ask me about any questions you have there. Appointments aren't mandatory this week, but I would love to talk with any of you that have any questions on the material. So get yourself ready for notes and let's get started. Today we're going to talk about describing the subsets of a given set. So we're going to start by defining subset and putting in some new notation. So the way that we write that something is a subset is like this. And this tells us that B is a subset or equal to, you can think of it as like an inequality, of A. Now what a subset is defined as is that every element of B is also an element of A. The way that we might write it in a more mathematical sense is that if B is an element of B, then B is an element of A. Like so. Now, the first thing we want to talk about is looking at, different definitions. So a clear definition would just be something like, oh, A, B is a subset of the alphabet. Right, I'm not going to write out every single letter. That would be the example of a subset. It's a part of a set. This is also helpful to think about in terms of infinite sets. So for example, if we think about the natural numbers, those are a subset of the integers. Every natural number is also an integer. The integers just also happen to have all those negatives and 0. And then the integers are a subset of the real numbers, which are in fact a subset of the complex numbers and so on. So we can fill in all of our different ones like that. Now, two really helpful facts about subsets. Obviously, I'm erasing. Please do not be erasing in your own notes. Apologize for not mentioning that earlier. Now, important facts here. We've got two that are really helpful is to say that using this definition, that the null set is a subset of any set A. So A could be any set you could imagine, the real numbers, a set of the alphabet, a set of colors. The null set is always going to be a subset of any set. And there's a proof by contradiction in the guided notes PDF that's attached here that I recommend that you look over. I'm not going to include it because I don't want this lesson to get too long. The other thing that's always helpful is that A is always a subset of itself by definition. Every element in A is also an element of A. So this is a helpful place to start when the assignment comes to write all subsets of A. So this is a set that contains 3 elements. It's a set that contains sets. So this is one of those times where I might write out the elements in a bullet list. We have the null set, we have the set containing 1, and we have the set containing 2. When I'm asked to write out all the subsets of something, I'm going to think about them in terms of going from the null set, which has the least number of elements in a subset, to the set itself, which has the most. So I'm going to start to say, okay, well, the subset with the fewest number of elements is the null set. And here's why this is a complicated example. The next one after that would be the set containing the null set, since this is an element here. So if I just said, oh, well, I'm just interested in this set, I'm going to erase these other 2, that's this one here. So these 2 are actually different sets. This is completely empty. This is the set containing it. Basically, imagine this is 0. This is you wrote the number 0 on a page. This is taking up space, whereas this is the concept itself. The next one would be have 1 element as well, and I'm just going to take the set containing 1. So this is similar logic. The last subset that's one element would be the set containing 2. So these are the first 4. The next ones I would count are the ones containing 2 of these elements. So I'm going to take the first 2, the second 2, and then the outer 2. So those are the 3 2-element subsets, and then the last one is just A by itself. So I've worked up from the smallest cardinality to the largest, and I know then, therefore, that my list is complete. These complete lists become, more challenging the more elements you have, but it's a nice way to organize your brain. Here it's saying we've got a set. And this is asking you to write all the sets of X, where X is a subset of A, B, C, and the cardinality of X is 2. So I might write that out in common English like this. So write all subsets of A, B, C with just 2 elements. Now, this is one of those cases where math is just a language that we need to learn how to understand and comprehend. There's a lot of symbols here, and you will get better at understanding them if you haven't already. So I'm going to start out with a big set. The first 2-element set I'm going to write is just A, B, just like the first 2. So it's the set containing A, B, that's the first subset. The second one is B, C. And then the third subset in this group would be A and C, similarly to what we saw in number 1. And that would be the entirety of this set, the set of X with a cardinality of 2. Now here is something that's going to be really important to theory as we go on, and these are proofs. Now proofs have a lot of different methods. If you looked at the proof of this fact here in the guided notes, you would see a proof by contradiction. In this case, we're going to talk about a proof by induction, which we talked about when you were all in my pre-calculus class 2 years ago, but I will give you a reminder of how these work, and we'll see several other methods of proof as well in this class. But we're going to start by induction for this one. Now, if you remember, the proof by induction follows 3 steps. The first one is proving that it's true for what we call a base case, which is usually prove that this is true for n equals 1. The next is to state, well, since it's true for n equals 1, then it must be true for some natural number. And this is what we call the assumption statement, and it's not necessarily any challenging math, but it is important to the proof. And then the final step is the actual algebra work of the proof, and that's to say that if it's true for k, k implies that it's true for k plus 1. Then we arrive at our conclusion, because if it's true for 1, and it's true for a consecutive pair, k and k plus 1, 1 would therefore imply it's true for 2, which would imply it's true for 3, 4, 5, 6, and 7, all the way on forever. And so then our last step we do is then we say therefore, which you might have seen as represented by 3 dots like this. Say therefore it's true for all n in the natural numbers, 1, 2, 3, 4, and so on. So this is how we set up our proofs, and we're going to start with that first step. So here we're going to prove it's true for n equals 1. Prove that if the cardinality of the set A is equal to n, then A has 2 to the n subsets. So if we're proving it true for n equals 1, what we want to say is that we know that the cardinality of A is equal to 1. We want to show that, therefore, it has 2 to the 1 subsets. So if that's true, I'm going to then say that that one element is A. A could be anything, could be a number, color, variable, another set, but we know that it has an element. Therefore, the subsets of A would be the null set and itself. This means that there are 2 subsets. Hence, we know that this is true for n equals 1. Now, the second step is we write that means that it's true for some k in the natural numbers. So the way I phrase this here, by this we can say that the cardinality of a equals k implies that a has 2 to the k subsets for some k in the natural numbers. Now, we know that at this point that's just true for this one, but that is in the natural numbers, so this is true. Now we're going to use that to prove that these consecutive sets are true. So the way that you always want to start this third step is either to say, all right, well, we're going to use k to show that k plus 1 is true, or show k plus 1 is true and work backwards. I tend to find that starting with the thing you know is true is a little bit easier. So the way I'm going to do that is I'm going to say, all right, well, we know that if this is true, if the cardinality of A is k, and A has 2 to the k subsets, so we know that this is true, we can then say that A is equal to something like 1, 2, 3, out to k. Now, of course, these might stand in the place of something else, but we know that this is going to be true for whatever type of elements 1, 2, and 3 are standing in the place of. I'm now going to define a new set that is very similar to A, but that has k plus 1 elements. So here we have B, which is all the elements of A plus just this one more term. So it's exactly the same as A, just a k plus 1 term right there. And with this knowledge, we can then say that the cardinality of B is equal to k plus 1. It's got all those elements, just one more. And here's where I'm going to do a little bit of talking versus writing, because I can talk a lot easier than I can write. So then we know that if every subset of A is also a subset of B, because we now can say that A is a subset of B. So all of its subsets are subsets of B. Everything in A is also in B like this. So the way we might write this algebraically is that any x is a subset of A, that x is also a subset of B. Alternatively, we can also say that if any x plus k plus 1 is another subset of B. Because we already implied that everything in X is in B, and we know that k plus 1 is in B. So here are the two different types of subsets that B has. Now, we know that there are 2k of these, and since there are 2k of X, there are also 2k of these types of sets. Therefore, the number of subsets of B equals those 2k plus 2k, the ones that are x and the ones that are x plus k plus 1. Add those together, you get 2 times k, 2 to the k, which is 2 to the k plus 1, which is the thing that we were trying to show in the first place, that if a set has k plus 1 elements, it has 2 to the k plus 1 subsets. So if you want to see this written out in full complete sentences, which is what I expect of you, I do encourage you to look at the PDF of the notes that are attached. Just in terms of this space and this medium, that's not as easy here. Please look at those for complete sentences. And so then we must write our conclusion. So if the statement is true for n equals 1, which it is, and consecutive numbers, k and k plus 1 are consecutive, then it is true for all natural numbers. Now, of course, there are going to be some proofs that don't make sense with natural numbers, but when we talk about cardinality, we are talking about the number of things in the set, which must go from, the null set out to anything countable like this. All right, let me know if you have any questions on these in the nomination form, or you can put something in the comments or make an appointment, and I look forward to seeing your number 14s attached here by the end of the week. Have a wonderful day. I'll talk to you later.